In this video, we're going to take a look at the origin for electric currents. And there are several ways that we can generate an electric potential and therefore charge flow. But the oldest form is the battery. So in this lecture, we're going to take a look at the nature of the battery and where the current comes from. Alessandro Volta was a 18th century Italian physicist slash crazy scientist, and found out that if you took two different kinds of metals and then let's say that you took these metals and you cut out two squares, maybe the size of a stamp or something like that, and then you made a sandwich out of these metals, and then the sandwich, the inside layer would be a piece of leather that had been soaked in salt water, and that's what the electrolyte was. And so he found that if he did a whole stack of these, like kept stacking it, let's say something like some really commonly found metals like copper and zinc. So copper, leather, zinc, leather, copper, leather, zinc, leather, and so on, and made a big sandwich like that, that the higher the stack got, that when he tried to connect two wires together, one connected to the bottom layer and one connected to the top, that he could get a little bit of spark. And then he also found that if he took some frog's legs and hit the frog's legs with these electrodes, that they would that they would jump. And then he got interested in reanimation and all sorts of crazy stuff. But anyway, that's where volts comes from, is Alessandro Volta. So really, it's just a classic chemical reaction, oxidation and reduction. And carbon zinc is the place where our most common and least expensive batteries are, but this technology has been around for a very long time. And this is actually a big issue about battery research as we become more and more dependent on them. And we'll take a look why in just a second. So we start off with a positive side and a negative side, and sort of this electrolytic solution in between. So the voltage that we're going to get on this depends on the chemistry that's happening. And essentially what we're going to have is we'll have the reactants for this chemical reaction are inside the battery itself. And then when we make a connection to the two terminals of the battery, we provide a path for charges to flow, and then we can harness that electric potential. So I'm going to just skip out of this for a second and take a look at a quick simulation. So here in our circuit construction kit, let's go ahead and grab a battery and grab a light bulb and make sure that we understand how this is going to work. So in order to make connections, I'm going to connect a wire to the base of the light bulb and then connect a wire to the side of the light bulb. Now, currently we can get LED light bulbs in this conventional package. So a lot of our fixtures are meant for these screw-in incandescent lights. And it's hard to retrofit all of those. But that's happening over time. If you get a more modern light fixture right now, then you're just going to wire the LED panel up directly. You're not going to have this weird socket thing. All right, you can see the direction of current flow, and I can change values. So if I increase the voltage and go up to something higher, you can see that the charge flow is much faster and the resulting brightness I get is higher. And we're watching electrons flow. So they're flowing from negative side to our positive side. We can switch to conventional current, and then we will see that current's flowing from positive to negative. The difference between electron flow and conventional current in large part is blamed on, or the mix-up between them is blamed on Ben Franklin, which is too bad because Ben Franklin's primary discovery, and I think we're talking around 1750, something like that, was that lightning was actually just static electricity. So he actually did fly kites, when the atmosphere was getting active, and was able to show that he could get sparks off of, uh, as long as his cord was soaked with water and was a good conductor, he could get sparks on the end he was holding, which is probably not a great idea because, had he triggered a bolt of lightning, he would have been killed for sure. Let's take a look at how modern uh, lightning bolts are detected. This is kind of a fun way of doing it. A model rocket is launched into a cloud and it drags behind it a thin copper wire. So let's see what this looks like. Yeah, you didn't see the rocket go, but it happened pretty quickly. So in slow motion, there goes the rocket, carries a coil of wire, and then the wire gets vaporized. So usually the launch of the rocket will be delayed until there's enough of a static electric charge in order to be sure that you're going to get a lightning strike. So the intention is you drag this wire up into a cloud, and then that provides a pathway for lightning to flow. And so you can actually get lightning to strike where you want it. But in this case, this is sort of an anomalous lightning strike. They triggered it, but it didn't follow the path of the wire. And if you take a look, there's actually considerably more current that flows. How fascinating in the way that the lightning branches out. Okay, good. So we'll stop that. And let's go back and just take a look at a little more detail on this. So I'm going to switch to, I'm going to stop sharing and then go take a look at my document camera. And just as a quick reminder, so here's my little sketch about what's happening. And in terms of labeling things, there were a couple of words that anode and cathode. And I just wanted to spend some time deconstructing these words. I'm always fascinated about where words come from in order to help understand their meaning. And ode shows up in both, like electrode. Ode stands for path or way. So an electrode is a path for electrons. And then these stems, or these prefixes, this means up, and this means down. So these definitely refer to the path of electrons, and these terms were coined by Michael Faraday. Who had several amazing contributions to what we understand about electricity and magnetism. Right, so what happens in our oxidation and reduction reaction is that this is where oxidation happens. So oxidation or rusting is the loss of electrons. And so that's why this, the negative terminal, is our anode. So this part is rusting. That's what oxidation is. And then over on the other side, we have reduction happening, which is the gain of electrons. And that's the cathode then. Right. So anode and cathode really are referring to paths of an electron. And we can switch back and forth between what we would call conventional current, which flows from positive to negative. But it's important to remember that the phrases anode and cathode and the actual chemistry of what happens that we recognize it's actually electrons moving from negative to positive. Right. Let's take a look at some battery chemistry. And in this simulation, what we can do is, well, let's label our battery parts here. So yeah, so we have sort of a barrier between two different materials, and these are the reactants of this chemical reaction. And we have a central carbon rod that goes through the battery that's going to be able to collect the current that flows. And so we'll see an electron transfer that happens as the anode gives up electrons to the cathode. So let's put this into play. Now, anode and cathode, we have zinc and platinum. So two dissimilar metals, and the nature of their valence electrons is a little bit different, so it can favor electron flow from one to the other. So let's take a look at and see what happens. So we have oxidation happening, and the zinc is giving up electrons. So as it gives electrons, that's why it's the up path. And you can see at this point, the reaction has stopped because the chemical reaction is over. All the reactants, most of the reactants have turned into products. Now, with this particular combination of metals with zinc and platinum, you can see we get a potential of just a little bit less than 2 volts. So let's try different cathodes here. How about this? Silver, we'll try that. Okay, so we get a slightly lower voltage with this particular combination. However, obviously the difference between platinum and silver is a pretty big difference in cost. And copper is probably going to be the least expensive. So let's take a look at what happens there. So if the anode is zinc and the cathode is copper, I get a potential difference of just a little bit over 1 volt. So I'm going to pause recording just for a second, and then we'll see what the other comes. So at this point, I've run through the different combinations of anodes and cathodes to try and see what we get. And when I start off with zinc, we get around 2 volts. Lithium has got a big kick. And of course, you know that lithium, if you look at its place on the periodic table, it's under the most reactive metals. So we get a big bang for our buck with the lithium platinum combination, but it sounds really expensive too. So after having run through all the combinations, we can see that lithium is actually a pretty hot topic. And so very small devices often have lithium polymer batteries. My rechargeable lawnmower has a lithium ion battery. And of course, electric cars have very large batteries. And we're about to see a real explosion in electric vehicles, but the research around batteries really has to get much better because lithium is very expensive. It's also very dangerous. And their supply of lithium is really not that great. So there is more attention being paid to research right now around using more cost-effective materials for batteries. It's also a really important point when we talk about our energy grid, because as we use renewables, as an example, solar panels do a great job on making electricity on a bright sunny day. But if the peak demand is at night, then we need a way of storing that. So let's go back and take a look at just some examples of batteries. Great, so we see a bunch of different combinations here. So here are just some traditional carbon zinc batteries coming in sizes AAA, AA. Here's a 9-volt transistor battery. Here's a rechargeable battery. Here's like looks like a D cell, right? But the actual voltage we get just depends on the electrochemistry. So for carbon and zinc, we're limited to about 1.5 volts. If we're trying to make a 9-volt battery, we stack 6 1.5 volts all together and put it in a little box. Your phones run on lithium batteries, and that's going to be around 3.3 volts. That's how come you can charge it by plugging it into a USB port, because the USB is at 5 volts. All right, so now we've talked about where voltage comes from. It's time to start making some current flow, and that'll be the topic of the next video.